Hi everyone. In this video, I am going to explain about the transistor switching times. So transistor switching times, previously I have explained how a transistor is acting as a switch. So transistor can be acting in three different regions. We have seen cutoff region, active region and saturation region. If you see the characteristics of this transistor, the three regions of operation of this transistor. So VI characteristics, VCE and IC, and joining these two gives the Q point, and this is the region where saturation region is there, and this is the region for the cutoff region. In between this saturation and cutoff region, we will be having active region. This is the active region where the transistor acting as amplifier. Now consider a circuit which is a transistor which is acting as a switch. This is the load resistor RL and a biasing supply VCC, plus towards collector and negative towards the ground. Here we are taking the output. This is the place we are collecting the output, and this is the input resistance RB. The current flowing through this resistance is IB, and here we are giving the input voltage plus minus. This is the ground. Okay, now if you see this particular transistor operation, this transistor is operating as inverter. This transistor is acting as inverter based on the input combination. Suppose if you are giving, suppose in digital if I speak, if I give 0 volts here, then transistor is acting as open circuit, because there should be a minimum cut-in voltage required to make this transistor on. Okay, this is the junction voltage. So base and emitter, this is the junction. There exists a diode. In order to switch on this transistor, it should maintain a minimum cut-in voltage of 0.6 or 0.7 for silicon and 0.2 or 0.3 for germanium. That minimum voltage is required to make the junction on. When this junction is said to be on, then the transistor is said to be operated in active region. If both the junctions are on, nothing but both junctions are like emitter junction and as well as collector junction, if both the junctions are said to be on, nothing but in forward bias condition, then the transistor is operated in saturation region. I told you already in the last video, there are two junctions. If both the junctions are forward biased, then transistor is said to be in saturation region. If one junction is forward biased, that means first junction, input junction is forward biased and output junction is reverse biased, then it is in active region. And if both the junctions are in reverse biased condition, then it is operated in cutoff region. What do you mean by cutoff? In cutoff region, transistor is in off state, open circuited. There is no flow of current. There is no flow of current. Simply the transistor is open circuited and output is exactly equal to the VCC. Output is exactly equal to VCC. Okay. And there is no current. I am saying there is no current. That's why you can mark this line as VCC. That is the reason why the point met here. Okay, and assume that the transistor is operated in saturation region where there exists a maximum amount of current flow, because it is acting as short circuit. It is acting as short circuit. What is the flow of current? This is the flow of current that is going towards the transistor. It is IC. Okay, so how can you write the IC? IC is nothing but VCC by RL. See, this is the load resistance RL. What is the path, the voltage path? So VCC by RL. That is the current flowing through the on transistor and as well as the resistor. So this is the point VCC by RL, which is nothing but IC, collector current. Okay, if you join these 2 points, that is known as load line. It is known as load line, which decides the VCE or IC, nothing but a bias point, nothing but a bias point. Okay, and in between these two regions, the saturation region and cutoff region, we will be having an active region where the transistor is acting as an amplifier. Suppose if you are giving input as 1 volt, output will be 2 volts or 3 volts depending upon the amplification factor. Okay, such type of characteristics you can observe in the active region in between these two, whereas this particular region is acting as saturation region, here it is acting as cutoff region in both the switching action. Switching action is taking place between these two regions, cutoff and as well as saturation. Okay, now what I am going to explain in this transistor switching times is, suppose assume transistor T1 initially is in off state. Listen clearly. Initially T1 is said to be in off state. Now I am giving the input, sufficient input voltage like VBE is equal to, now let it be 1 volt I am giving. Minimum required potential is 0.6 or 0.7 depending upon the type of the material, silicon or germanium. Suppose I am giving a junction potential such a way that the junction will be having a voltage of 1 volt. I am giving the input voltage such a way that the junction will be having a potential of 1 volt across the base and emitter. So this 1 volt is sufficient to switch on the transistor. Now I am saying that as this is the input voltage appeared at the junction of the transistor, T1 is said to be in on state. T1 is said to be in on state. But how much time it will take to switch on from the off state after giving the 1 volt supply? This is the switching time. So switching time is nothing but how much time that the transistor will take to switch on from off state and as well as to off from on state. Okay, that means the switching action is taking place between off to on and as well as on to off. But what is the total amount of time taken by the transistor to change from on to off and as well as off to on? We are assuming the practically, okay, it is taking 0 instant. Ideally we can say 0 time instant, 0 seconds it takes and immediately to switches from 0 to off to on and on to off. But practically it is not the case. Definitely some amount of time lapses between these two states. Okay, I am not saying off to off. Definitely it will take from on to off and as well as off to on. Okay, there are generally 3 different time instants we can study here. One is delay time. Delay time indicated by TD, and second one rise and fall time, we can say rise time and fall time, we can say rise time is indicated as TR and fall time is indicated as TF. And third one is storage time. Indicated by TS. These are the 3 important timing factors that we should consider when the transistor is switching on from off and as well as off to on. Okay, now first one is the delay time. What do you mean by delay time? This is the time taken by the transistor to respond for the input condition. Hope you understand. Time delay is nothing but some delay. Suppose someone asked you a question, what is your name? Or immediately after you answered the first question, they have asked you another question. Okay, so definitely you will take some time to understand the question and as well as to answer it accordingly. Okay, so for that time lapses between the question, completion of question and the start of answer is nothing but your delay time. So here also transistor is initially set to be in off state, but if you want to make this on, you are giving a supply of 1 volt, but transistor should realize that it should on. It should realize. So the time taken by the transistor to realize or to respond for the input voltage is nothing but your delay time. Coming to rise time and fall time. Rise time and fall time, by seeing the names you can understand. Already you might have studied the terms rise time and fall time in the earlier classes of the same pulse and distortion circuits. So rise time is nothing but the time taken by the transistor to change its state from 10% to 90%. Suppose if the transistor is said to be in off, then it comes into on, so that the output voltage is slowly decreasing. And assume the transistor initially on and it is coming to off, then output is increasing, because when transistor is applied with 0 volts, then output is 1, and if the transistor is given with 1 volt, then output is equal to 0. So whatever may be the state, suppose if the output goes up like this, the time taken by this state is nothing but 10% to 90% change is nothing but your rise time. Okay, and the same opposite case you are studying now as fall time. Fall time is nothing but changing the state of the output from 90% to 10%. This is what a fall time is referred to. So rise time is referring to a state when changing from 10% to 90%. See, in order to study rise time, the output should increase. That means input should be 0. Input should be changing from 1 to 0 like this, and output should increase. In order to study the fall time, you can understand once if you see the diagram. I will show it to you. Input should be changing from 0 to 1 and output is going like this, because it is acting as, I already told you, it is acting as inverter. So this change is nothing but fall time. So rise time is the time taken by the transistor to change its state from 10% to 90%, as well as we can say the fall time is nothing but changing the output signal from 90% to 10%. Coming to another important timing factor, which is nothing but storage time. What do you mean by storage time? Storage time is nothing but the input, of course, it is changing from 1 to 0. Okay, but still that particular voltage which is having across the transistor, that will be lapses for some duration. It immediately will not lose its charge. Okay, that particular value will be sustained by the transistor for some time. This is what the storage time. So these are the three different timing factors that are generally coming across in the transistor switching actions. See the relation between this IC VI with respect to this timing diagram. See, input I am giving as the waveform like this. See, input is having two different states. One is V1, which is a negative voltage, V2 is a positive voltage. Now, initially the transistor is set to be in on state. At this particular instant, let it be at T1. Now we are at a T1 position. So at T1, what happens? Input is applied a positive voltage. So the transistor is set to be in on state. See, before T1, the transistor is having a potential of negative voltage, which is minus V1. It is a negative voltage. It is a negative voltage. As it is a negative voltage which is applied at the input of the transistor, simply transistor is in off state. Transistor is in off state. So there is no current. As the transistor is in off state, open circuited, no current is there. So IC is equal to 0. IC is equal to 0. But exactly at t is equal to t1, what happens? There is a sudden change in the input from 0 to V2. V2 is a positive supply which is sufficient to switch on the transistor. So transistor now it is coming into on state. But see, it is not immediately changing its state. It is not immediately taking the current. It slowly takes the current across this junction. Slowly current increases. Whenever the current reaches 10%, up to that instant, it is called as delay time. It is called as delay time. What I told you in the delay time? Delay time is the time taken by the transistor to respond to the input. So the input has given at t1 instant, but after t1 plus td seconds only, the output starts rising. That means the current starts flowing through the transistor. The time taken by this particular device is nothing but delay time. Now coming to the rise time. Rise time is nothing but the time taken by this current IC changing from 10% to 90%. See, 10% of this saturation current to 90% of this collector current saturation current. Again, see here, at t is equal to t2, what happens? There is one more sudden change from positive to negative. So the transistor has to again come back to the switch off state. But immediately it will not come. It stores that same current, whatever it has been passing through, then it maintains that current for some duration. That duration is nothing but storage time. So storage time is the time taken by the transistor to leave the current IC. Okay, so previously it is having a maximum current flow across it, but it takes some time to leave the current. So whenever it starts leaving, again fall time came into existence. So TF is the time taken by the transistor, time taken by the collector current to change its state from 90% to 10% of its maximum value. Okay, this is what the description of the different time instants of the particular transistor operation in a switching action. Thank you.